Hello everyone, myself I am TP Aditya, pursuing my Bachelor of Engineering in Electronic and Communications at Welltech Multitech College of Engineering. Today I am here to present our project, Design of an FIR adaptive filter for biomedical applications, along with my teammates V. Karthik and P. Susan, guided by Mr. D. Ruben Thomas. Let's get into our objectives. The objective of the project is to design a high-performance adaptive filter using distributed arithmetics. Improving the performance in a filter is a challenging task. We have improved the performance and reduced the complexity in this project. To improve the performance, we have used carry look ahead adder and radixate boot encoder velocity multiplier. Let's get into the introduction. In signal processing, a filter is a device or process that removes some unwanted components or artifacts. Commonly, filters used to remove some frequencies or frequency bands in a signal. There are different types of filters in digital signal processing. The widely used finite impulse response and infinite impulse response filter, which is FIR and IIR. In this project, we use FIR filter because they have a stable value and there is no limitation for the cycle and analog history. Literature survey. These are the surveys we have done to gather information about the filter and distributed arithmetics we have used and about the performance and implementation in our project. Let's get an overview of FIR adaptive filter. FIR adaptive filter commonly has two modules, error computation module and weight update module. When the coefficients of filter in the weight update module are updated automatically, the weights are determined using an adaptive filter algorithm least mean square. This is a basic block diagram for an FIR adaptive filter where X of n is an input signal which is passed through an FIR adaptive filter. It produces an output signal Y of n, where D of n is a desired signal where the desired signal and output signal from the FIR adaptive filter are summated or compared and gives an error signal which is E of n. The output signal is then passed through a weight update module where it updates the weight of the given signals by making delays within them. Let's get to know about the least mean square algorithm or LMS algorithm. LMS algorithm is a class where it mimics a desired filter by finding the filter coefficients that relate in producing least mean square of error signal. The algorithm for pth order can be represented as where p is the filter order, mu is the step size, h cap is an initialization value. Initialization values is equal to the zeros of the pth order. X of n is an input signal where it can be increased for as many inputs. E of n is an error signal where error is found by comparing the desired signal along with the input signal. H cap values can be increased by the step size values along with the error signals where it is an integer used for ECE analysis. This is the block diagram of error computation module where ECM helps to compute the error signal by comparing the desired signal and the actual signal. In this, X of n is an input signal which is passed through a delay D and the signal is delayed into X of n minus 1. The process will be repeated for the number of inputs given. The input signals are sent to radixate booth encoder multiplier. In this, W of n are the integers given for ECE analysis where it can be shifted easily to the fixed point. In radixate booth encoder multiplier, the integer W of n is encoded by booth encoding which acts as an multiplier and the input X of n or multiplicand. We get the partial product and forms an velocity formation and it is passed to carry look ahead adder where desired signal is added and compared and produces a product of ECM which is Y of n and which will be the input for the weight update module. This is the block diagram of weight update module. The same process from the error computation module will be taken place here, where the coefficient of integer mu into E of n is used. Mu is the step size of the filter and E of n is the integer which can be easily shifted to its fixed point which acts as an multiplier in radixate booth multiplier along with the W of n, and CLA sums the product and produces the weight of each product or each signal. Let's see the outputs of ECM, WM and the overall analysis of FIR adaptive filter. This is the waveform for ECM for 8-tap adaptive filter where D often is a delay signal, E often is an error signal, X often is an input signal, Y often is an output signal. The area covered by the ECM of proposed data adaptive filter is 267 logic elements, where logic elements is known as the logic cells or the area. The time taken for an ECM of proposed data adaptive filter is 7.883, where TSU is a setup time, TCU is a clock to output delay, TH is an output time, TP is an propagation delay. The power taken by the 8-tap adaptive filter for ECM is 215.11 milliwatts. This is the waveform for weight update module for the 8-tap adaptive filter, where W0 to W8 represents the different weights for different inputs, where 8-tap represents the 8 inputs of this filter. There are 8 different weights given. The flow summary represents the total area or total logic elements acquired by the weight update module. It's 76, and the time required for the weight update module for the proposed data adaptive filter 4.154 ns, and the power taken by the AWM for 8-tap adaptive filter is 225.96 milliwatts. And the overall analysis for an proposed 8-tap adaptive filter, the flow summary is given for an proposed 8-tap adaptive filter, where the area covered by the proposed 8-tap adaptive filter is 97 logic elements, and the time taken is 8.096, and the total power consumed is 206.64 milliwatts. This is the waveform for air compression module often proposed 16-tap adaptive filter, where 16-tap represents the 16 inputs of the filter. The same process is continued here. The area is measured. The logic elements taken for the 16-tap ECM is 514, and the time delay is 6.542, and the power consumed is 254 milliwatts. And the same process is carried on with the weight update module, where it has an 16 weights from 0 to 15, represents the different weights updated by the LMS system in an FIR adaptive filter, where logic elements represents the 156 or area. The time taken is 5.235, and the power consumed is 301.25. And the overall analysis of an 16-tap adaptive filter is proposed here. The waveform is given along with the area or logic elements 549, and the time taken or delay is 3.350, and the power consumed is 232.34 milliwatts. And the same way is taken up to 64 bits of an adaptive filter, where the performance is increased when compared to the existing system. The performance of the 64 adaptive filter is, the area covered is 642 logic elements or logic cells, and the time taken is 9.943 nanoseconds, and the power consumed is 165457.85 milliwatts. The same method of ECM, WM, and the overall analysis done in 8-tap adaptive filter is used by 16-tap, 32-tap, and 64-tap, and gives the area, time delay, and power used by the proposed adaptive filter. And the comparison table for the existing and proposed adaptive filter is given here, where it represents or denotes the improvement in the proposed adaptive method. Let's check for the 64 adaptive filter, where the area covered in the proposed adaptive filter is 640 logic elements, whereas in the existing adaptive filter for 64 tap is 849, where it is reduced by 209 logic elements or logic cells. And the time delay taken here in the proposed adaptive filter for 64 taps is 9.943, whereas in existing system it is 14.473. The time delay is reduced by 3 seconds or 4 seconds tremendously. The power acquired in the 64 tap adaptive filter is 1395 milliwatts, whereas in the existing system it's 1632, where it is reduced by 300. And the process will be repeated for the multiple inputs as for 128 taps if you require. As I have practiced this method in an small circuits or small level for signal processing, It can be used in biomedical applications and other digital signal processing applications. These are comparison tables for existing and proposed methods where we can clearly see the difference in time delay, area, and the power consumed by the existing and proposed method. It is done in a smaller level. If the filter is implemented in a higher level, it provides a high performance and reduces the complexity in most of the DSP or biomedical applications. These are the comparison graphs for the 8 tab, 16 tab, 32 tab and 64 tabs, time analysis, power and the area for the given adaptive filters. This graph clearly shows the difference level between the proposed adaptive filter and the existing adaptive filter, which proves that the performance in our project has increased and the complexity is reduced when compared to the existing FIR adaptive filters. So these filters can be used to detect the signals, to detect or remove the unwanted artifacts or frequency bands from a signal in a biomedical applications. Let's take an example of EEG signals or ECG signals. When a signal is passed through the filter, the filter amplifies and reduces the artifacts in a higher level when compared to the existing filter. By reducing the noise, we can know the clear problem in our body or the signals. Let's get into the conclusion. The proposed FIR adaptive filter can be implemented in biomedical applications and digital signal processing. In biomedical applications, the FIR adaptive filter is used to detect or remove the artifacts or noise produced from the EEG signals, ECG signals, and ENG signals, and the different kinds of signals can be filtered by reducing the artifacts and noises and gives the pure signal where it shows the clear knowledge of the problem in our body. And in digital signal processing, these FIR adaptive filters is used to reduce higher frequency bands accurately and give the accurate values for the digital signal processing. These are the references which are taken for our projects and which was helpful in improving the FIR adaptive filters performance and reduce the complexity. This is all about our project. Thank you.